In Chapter 2, we review the concept of a function. A function is a mathematical construct that you've looked at quite a bit in high school, and it's the essence of what calculus is. Calculus is a math that's used to analyze functions. So we're going to start off in Chapter 2 by just making sure that you understand what a function is and the notation that's used with it. So in 2.1 we look at function notation. Now I'm going to give you a definition of a function a little bit later, but the best way that I can explain a function to you is this idea of a function machine. It's, I think, a really wonderful idea in understanding what a function actually does. So what is a function machine? Well, just imagine that we had a box here. In that box, inside of it there were some gears, and that box had been programmed to take numbers that had been thrown into it and perform operations on them. So we need to give our function machine a name, so let's say we called it f for function. Now what we're going to do is we're going to throw numbers into this machine. So let's say, for example, we threw the number 2 into our machine, and then we gave our machine a crank and we just churned out some answer from that number 2. So let's say the machine kicked out the number 5. So what's happened is the number 2, which is called an input, has been put into a machine, and the machine has applied some rule to this number, and the output was the number 5. Now it's hard to tell what the machine is doing to the number based on just one input. So let's say we threw another input into the machine. Let's say we threw in the number 4, and the machine did its thing. Now you can't change what's going on in the machine. The machine has been programmed to do something, and that something is called f. And let's say the machine kicked out the number 9. Now maybe you can see what's happening at this point. So what if instead of throwing in a number like 2 or 4 or any other number, what if we threw in an arbitrary number called x? If we threw x into the machine would take that number x and it would apply whatever is inside the box to that x. And the way we would indicate that is we would say the function f is taking the number x and creating an output. So these numbers right here, these numbers are called the inputs. Collectively we call them the domain. The domain is simply the set of all inputs into your function. And then the result that comes out is called the range. So all of these numbers right here we refer to as the range. Now can you see what's actually happening? For every number that's being put into that machine, the machine has been programmed to take that number, double it, and then add 1 to it. So we can express that algebraically as 2x plus 1. So this is an example of what's called a function. A function is simply a rule that applies to a certain set of inputs. So in this case we would say the function f, which is this machine right here, for any value of x, or the way you would read that is just f at x, is equal to, and then we would write 2x plus 1. Now you're probably familiar with this. You've studied function notation before, but I think the function machine gives a really good indication of what's actually happening. This particular function right here, if you actually graphed all of these points, that's all a function is. It's just a bunch of points. There would be a point, in this case, there would be a point at 2, 5. There would be a point at 4, 9. And there would be a point at x, whatever the function is being told to do to the x. So f at x. In this case, if you actually plotted all these points, you'd notice that they would fall on a straight line. And so this is an example of what's called a linear function. Okay, so we'll just try this again. So let's say we had a different machine. So again, the machine is just meant to be an analogy of what's actually happening. So let's say we had a different machine, and we called this time the machine G, indicating that it's a different rule than the original machine F. So in this case, let's say we threw in the number 2, and the machine kicked out the number 4. And then we threw in the number -2, and the machine also kicked out the number 4. So can you see what's happening there? I picked this example because I wanted you to see that you can, in a function, have different inputs into the machine, and the machine can, as a result, kick out the same number. And so what's happening in this case is if you threw in some number x, all of the numbers that are coming out have been squared. So our machine would be g at x is equal to x squared. So you'll notice again, and I want to stress this, that it's possible to have two different inputs. Okay, so we can have different inputs resulting in the same output. And you can see how that could happen. I mean, just the machine has been programmed to do something to the numbers, and in this case, it's possible to throw in two different numbers and have exactly the same result come out. And the reason why I drew this to your attention is what would happen, can you imagine this situation? Can you imagine a machine, and inside of it is some kind of rule that we don't know what it is, and can you imagine throwing the number 2 into the machine, and the machine kicks out the number 4, so that's more than possible. But what if you threw in the number 2 a second time, and the machine kicked out a different number 5? If you think about it, that doesn't make sense. If you haven't changed what's going on inside the machine can't take the same input and do two different things to it. I mean, unless you actually went inside the machine and changed the rule. So that's why probably at some point, so this is impossible. At some point, I'm sure you've been given a definition of a function, and there's lots of definitions out there. The definition itself is not something that I would say is really important for you to memorize, but a function, I'll just give you the definition now. A function is a set of ordered pairs You can see in this first example and in the second one that all you're going to get when you throw numbers into a function, when you get an output, together they can be collected into an ordered pair. So you could actually graph all of these ordered pairs. In this case, you could graph all of these ordered pairs. In the first example, the ordered pairs would be a straight line. The ordered pairs would just look like this if you put them all together. In our second example here, you may recognize x squared as just a parabola. So our graph would look like this. But really, a function, if you draw a graph of it, you can see that it's just a bunch of ordered pairs. But what's important about the ordered pairs, it's a set of ordered pairs in which every member of the domain, so all of the inputs, okay, those are called inputs, is paired with one and only one member of the range. Which of course are the outputs. So that would be a formal definition of a function. You may have learned different strategies for determining whether you have a function. One of the strategies is called the vertical line test. I'll just take an opportunity to maybe remind you of that. If you look at the graphs of the functions that I've drawn for you, if you take this linear function right here, we know that we can't have 2 points directly above each other because 2 points directly above each other would be the same input giving 2 different outputs. So if you draw a vertical line through this graph, you'll notice that the vertical line only passes through the graph at most one place. That's how you can tell if something is a function. So something called the vertical line test. If you have a function, a vertical line can only cross the graph in one place. Same with this graph right here. Every member of the domain has its only one unique member of the range. If you were to graph this situation right here, the point 2,4 and the point 2,5 would be directly above each other, and that would fail the vertical line test. So the idea of a function machine is just an analogy used to help students understand, because in calculus, when you get into the calculus in chapters 3 and so on, we're going to see that a function is really the mathematical idea that we use all the time. So we'll just do a little bit of practice here with function notation. So we'll finish off this section by just looking at a couple of examples. And really the point of section 2.1 is just to get you comfortable working with function notation. So what I've done in our first example here is I've given you a function. The function is the function f of x, which again just means that we have some rule, and the rule has been given to us. It's x squared minus 3x, and the function symbol, the function notation symbol, is simply saying that the function f at any value of x, of any input, would just be x squared take away 3x. And I've taken you through 3 situations here. Often we just plug numbers into functions. The input would just be a number. So in this case, you would read this as, what's f at 2? In other words, what would you get if you took the number 2 and threw it into the function machine? So the way you would write that is you would just say f at 2 equals, and then you would simply replace the x with the input. It's important that you use brackets when you replace the x, because your input, sorry, that's a positive. What I was thinking was if your inputs are negative, then you want to make sure you use brackets. So you can see that if this had been a negative 2, if you didn't put a bracket around this, then you'd get an incorrect result. So just make sure you always use brackets when you're placing your inputs into a function. So we would just say the function f at the input 2 is equal to 2 squared minus 3 times 2. So we would just work that out, and we would get 4 minus 6 or minus 2. So again, if you looked at your function machine, if you like that analogy, the machine is called f. If we throw the number 2 into the machine is kicking out the answer, negative 2. So there would be an ordered pair on our graph at 2, negative 2. But it's also possible to throw variables into a function. So this is saying, what would the function f equal if you put the input c into the function? Well, it doesn't matter whether it's a number or a variable. It's the same process. You would just go c squared minus 3 times c. Now, in this case, of course, you're not going to get a numerical value. You're going to get a variable expression. But your output would be c squared minus 3c. So if you took this function f and you threw in an arbitrary value called c, then the output would just be c squared minus 3c. And you're going to see later when we get into the calculus part of the course that often in functions we plug in expressions that are more than one term. So in our last example, I've asked you to evaluate the function f at the point 3 plus h. Well, again, it doesn't really matter what's inside the bracket. The process doesn't change. You're going to take the function f, you're going to put the input 3 plus h in, and the output is going to be 3 plus h all squared minus 3 times 3 plus h. Now, in a situation like this, you would probably simplify your expression. So 3 plus h squared just means 3 plus h times 3 plus h, which would be 9 plus 6h plus h squared. Distributing the minus 3 into the bracket, we get minus 9 minus 3h, and our result would just be 3h plus h squared. So the number inside the bracket is called the input. The result that you get would be called the output, and together they make an ordered pair on our graph. So function notation is fairly straightforward. It's fairly simple to use. It's just a nice way of summarizing what a function is. Maybe just another comment. The function symbol is handy because it allows you to show what you're plugging into the function. Just so you know, you can use the letter y. Often we would just write a function as y equals x squared minus 3x. That's something that you're probably familiar with as well. The only problem with using y is, if you wanted to plug a number into the function, how would you express it? How would you show that? What we do in that case is we go y at, and then let's say x equals 2. And then, as we did up here, the answer would be -2. You can see that that's not as convenient. We prefer almost exclusively in calculus to use function notation when working with functions. Now, the second example is simply working backwards. It's important that you are able to read a graph. So what I've done in this question is I've given you a graph of a function. So this is just some function called f. And I've indicated some of the points on the graph with these dots. And the question is saying, find the function at 2. Now again, the reason for this question is we obviously don't know the rule. We don't have the rule that's telling us what the function machine has been programmed to do. But we can still read off the graph and see what the output would be. If we were to plug 2 into our function, so there's x equals 2, the output would be the y value. So if you look at this point right here, this is 2, 0. So if I plug the number 2 into my function, the output would be the y value, or 0. So this would just be 0. The next question says find f at -1. So again, we just go over to -1. We're looking at this point right here. This point is -1, 1. So our answer would be 1. And the last question, a little more thought-provoking, for what values of c, so now we're saying what numbers would you have to put into the function called c that outputs of 2? So just again, making you think a little bit about what's going on here. So the y value, your answer is always the y value. The function value is the y value. So I'm looking for where on this graph could I throw in a number called c and get an output of 2? Well, the output of 2 would be all the y values that are 2. Well, here's y equals 2. If you drew a horizontal line right through y equals 2, you would see that it's hitting the graph in 2 places. Those 2 places would be our inputs that would give us that value. The first input would be x equals 0. This point right here would be 0, 2. And there would also be a value right here at 3, 2. So in this case, c could be 0 or c could be 3. Okay, so that wraps up our study of function notation, which is basically the beginning of Chapter 2, which is the review of functions, which of course is going to be critical once we get to the study of calculus.